Okay, so have you ever really sat down and tried to make sense of building regulations?
Oh, yeah.
Like all the rules and the guidelines they have to follow? I mean, it's a lot, right?
Absolutely. It's a massive undertaking. And, anyone who's worked in architecture, engineering, and construction, like in the AEC world, they know exactly what we're talking about.
Yeah, it's so time consuming, all those manual checks, and it can be a real drain on resources. And honestly, even with the best intentions, sometimes things slip through the cracks.
Right. Human error is always a factor.
Exactly. So wouldn't it be amazing if we could find a way to automate that whole compliance
Oh,
process,
for sure.
make it faster, cheaper, and a lot more accurate? That's exactly what we're diving deep into today.
Yeah. And this is not just about making things easier for the AEC folks. I mean, it has a real impact on the buildings themselves, right?
Absolutely.
We're talking about making sure that the places we live and work in are actually safe and functional and meet all the standards.
Right. So it's not just an efficiency thing, it's a safety thing.
Exactly. It's about taking that crucial stage of compliance and bringing it into the 21st century with the power of automation.
And we're not talking about some far-off futuristic concept here. I mean, we've already seen some really cool tools come onto the scene, like building information modeling BIM.
Right.
That's been a game changer in a lot of ways. And we also have these rule-based systems that can actually check those digital models.
Absolutely.
They've definitely helped catch non-compliance early on, but there have been some roadblocks.
Yeah, sure.
One of the biggest is the need for super standardized data. I mean, it's like trying to get everyone to speak the same language with the exact same dialect.
Yeah, it's a huge challenge.
And then on top of that, you have the sheer complexity of the regulations themselves.
Oh, absolutely.
It can be really overwhelming.
So this is where the requirement applicability selection and exception methodology comes in, or RASE as it's commonly known.
Yeah.
This has emerged as a really promising way to tackle these challenges.
Okay, so RASE, R-A-S-E.
Exactly.
That's the acronym.
It's all about taking those massive legal documents and breaking them down into manageable chunks.
Okay, so let's break it down.
Sure.
RASE, we've got requirements, applicability selection, and exception. What does that actually mean in plain English?
All right, so think of it this way. The must-dos, the things you absolutely have to do in a building, those are your requirements. Then you have applicability, which tells you when and where those requirements apply. Makes sense, right?
Yeah, so it's like the if this, then that part.
Exactly. Then you've got selection, which kind of broadens the scope. It's like saying, okay, this requirement applies here, but it also applies in these other situations. And finally, you have exceptions, which are basically the unless clauses.
Okay, so exceptions are like the loopholes.
Yeah, you could think of it that way.
Okay.
It's saying this requirement doesn't apply if these very specific conditions are met.
So it's like a really systematic way to make sense of all this legal jargon.
Exactly. RACE provides a structured framework to analyze those regulations and extract the essential information.
So instead of getting lost in a sea of legal text, you've got this nice organized system.
Right, and this makes it much easier to then translate that information into something a computer can understand and use for automated checking.
Which brings us to the heart of our conversation today.
Okay.
We're going to explore how AI, specifically large language models or LLMs, are being used to automate that race annotation process.
Yeah, this is where things get really interesting.
So these LLMs, these are the systems that can understand and even generate human-like text.
Right, they've become incredibly sophisticated.
In the research we're looking at today, it dives into how these models can be used to grapple with those complex regulations and turn them into something a computer can use for checking.
It's like teaching the computer to speak regulation.
Exactly. So our mission today is to see how this cutting-edge approach works, what it's capable of, and what kind of potential it has.
Sounds good.
Okay, so let's get into it. What was the main idea the researchers were exploring here?
So traditionally, race annotation has been seen as this very complex task, requiring deep understanding of language and the legal nuances.
Lots of expertise.
Exactly. But these researchers, they took a different approach. They reframed it as a text generation problem.
Interesting. So instead of trying to get the computer to understand all the intricacies of the regulations, they're essentially saying, hey, can you just generate the correct output based on this input?
Exactly. And for this, they used OpenAI's GPT-4o, which is a really, really massive and powerful LLM. It's like the super brain of language models.
Wow. So they're really bringing out the big guns here.
And GPT-4o is known for its ability to process and generate text in a very nuanced way.
So they feed this LLM the raw regulatory text, and they want it to spit out RASE annotations, but in what format?
YAML. It's a structured data format that's both human readable and machine readable.
Okay, so it's kind of like a bridge between plain English and computer code.
Exactly. YAML is perfect for this because it allows you to represent the RACE annotations in a very organized way. It's not just highlighting keywords, it's creating a structured output with all the necessary information.
So the LLM is not just saying, oh, this is a requirement. It's actually creating this structured output that includes this specific text being annotated and all the metadata that defines the RACE scheme.
Right.
Yeah.
And it's this metadata that allows you to eventually generate those automated rules.
I see. So YAML, it's kind of like the secret sauce that makes the whole thing work.
You could say that. It links the natural language of the regulations to the formal language that computers need for checking.
Okay, now the researchers didn't just try one way of teaching this to the LLM. They actually investigated different learning techniques.
Yeah, they wanted to see which one would be the most effective.
So what were those techniques?
Okay, so the first one they tried was few-shot learning.
Few-shot learning. So that sounds like they gave the model just a little taste of what it needed to do.
Yeah, exactly. They gave GPT-4o just 3 examples of regulatory text that had been correctly annotated with RASE in that YAML format.
So it's like showing someone a few phrases in a foreign language and then asking them to translate a whole document.
Yeah, it's a bit like that.
They might get some of it right, but the grammar and the structure could be all over the place.
And that's kind of what happened here. The model showed some basic understanding. It could process the text to some degree, but it really struggled to get the structure of the YAML output correct.
So it was like it had the vocabulary, but not the grammar.
Pretty much. And that's understandable given how few examples it had to learn from.
Okay, so then they moved on to a more robust technique called fine-tuning. What did that involve?
So fine-tuning is all about taking a pre-trained LLM, like GPT-4o, and training it further on a more specific data set.
So it's like taking a student who's already got a good general education and then giving them specialized training in a particular field. Exactly. In this case, they used 15 pairs of regulatory text and their corresponding YAML annotations for training and another 5 pairs for validation.
Okay, so that validation set is important to make sure the model isn't just memorizing the training data.
Absolutely. It's got to be able to generalize to new examples.
So this fine-tuning process, it essentially fine-tunes the internal workings of the model, making it much better at RACE annotation for building regulations.
Right. The more examples it sees, the more effectively it learns those specific patterns and structures.
So like anything else, practice makes perfect.
Yeah, and that leads to better accuracy both in the content of the annotations and in how the information is organized in the YAML output.
Okay, and then they had this third technique which sounded even more advanced, progressive active learning. What's that all about?
Okay, so progressive active learning takes that fine-tuning concept and adds a really important element, human feedback.
Oh, so it's like having a teacher there to guide the learning process.
Exactly. It starts with the initial fine-tuning, but then the model's predictions are evaluated.
If the model is super confident in its annotation, meaning it meets a certain accuracy threshold, then those high-confidence predictions are reviewed by human experts.
I see. So the experts are basically double-checking the model's work.
Right. And if they find any errors, they correct them. And then those corrected examples are fed back into the training data.
So the model is constantly learning and improving based on expert feedback.
Yeah, and the progressive part of the name emphasizes that the model gets better with each cycle. And the active part refers to the fact that the model is actively seeking out that feedback.
So it's a very dynamic learning process.
Exactly. In this study, they went through 3 of these feedback and retraining cycles. And as you might expect, the model's accuracy improved significantly with each iteration.
Okay, so that's really cool. But to really understand how this all works, we need to go back to the RACE scheme itself. You mentioned those 4 core operators: requirement, applicability, selection, exception. Can you give us a little more detail on each one?
Sure. So the requirement is the most basic element. It's the rule or the check that needs to be satisfied, and it's often signaled by words like must or shall.
So like the building must have a fire escape.
Exactly. Then you have applicability, which defines the conditions under which that requirement applies. It's like saying this rule about fire escapes applies to buildings that are over a certain height.
Okay, so it's adding context and specificity.
Exactly. And almost every requirement will have at least one applicability linked to it.
Makes sense.
Yeah.
What about selection? How is that different?
Selection kind of broadens the scope of the check. It's like saying, okay, this requirement about fire escapes, it applies to tall buildings, but it also applies to buildings that have a certain occupancy level.
So it's expanding the range of situations where the rule applies.
Right. And then finally, you have exceptions, which are the unless clauses. It's saying this rule about fire escapes doesn't apply if the building has a sprinkler system.
So it's like carving out a specific exemption from the general rule.
Exactly.
Okay, so we've got requirements, applicabilities, selections, and exceptions. Now, you said some of these are more common than others in regulatory texts.
Yeah, that's right. Requirements and applicabilities are definitely the most prevalent because they form the foundation of the regulations.
It's like the bread and butter of regulatory language.
Exactly. Selections and exceptions are a bit rarer because they deal with more specific situations.
So once you've identified these different RACE elements within the text, how do you actually turn them into something a computer can use for automated checking?
Okay, so there's a 3-step process.
Okay.
The first step is to add markup to the text based on those 4 RACE operators.
So it's not just about highlighting the keywords, it's about adding specific tags to indicate the different elements.
Right, and it's also about capturing the hierarchical structure of the text.
So like how the different clauses and subclauses relate to each other.
Exactly. Regulatory documents often have a lot of nesting. Like a main requirement might have several subconditions, each with its own applicability. And the RACE markup needs to reflect that.
Okay, so it's about preserving the logic and the flow of the regulations.
Exactly. The markup has to be very precise.
So that's step 1, adding those RASE tags. What about step 2?
Okay, so step 2 is all about adding metadata to those tags. And for this, they use the OTCVU scheme.
OTCVU. Okay, break that down for me. What does that stand for?
It stands for Object Target Property Comparator Value in Unit.
Okay, so 5 elements.
Right.
What do those elements represent?
So the object is the thing being regulated like a door or a window.
Okay.
The target or property is the specific attribute of that object that we're interested in, like the width of the door or the height of the window.
So it's getting really granular.
Yeah, and then you have the comparator, which is the type of comparison being made, like greater than, less than, or equal to.
Okay.
The value is the specific quantity or measurement, like 800 millimeters. And finally, the unit is, well, the unit of measurement, like milliliters, meter, or whatever it may be.
So it's like creating a very precise set of instructions for the computer.
Exactly. And this level of detail is what allows the system to go beyond just understanding the words and actually perform a check.
Like actually measure the width of the door and see if it meets the requirement.
Exactly.
Okay, so that's step 2, adding the OTCVU metadata. What about step 3?
Okay, step 3 is where all of this comes together to form a usable rule. And for this, they use Boolean logic.
Boolean logic, that sounds complicated.
It's actually not that bad. It's basically about combining those annotated elements using ADOR and not operators.
Okay, can you give me an example?
Sure. So let's say you have a requirement that says a door must have a minimum width of 800 millimeters.
Okay.
And let's say there's an exception that says unless the door is a fire exit.
Okay.
So using Boolean logic, you could represent that rule as door width greater than or equal to 800 millimeters and not fire exit.
So the computer can easily evaluate that statement and determine if a particular door meets the requirements? Okay, so that's how they transform those RASE annotations and OTCVU metadata into a machine-readable rule. But all of this still relies on having those initial annotations. And as we discussed, that's where the LLMs come in.
Yeah, traditionally, those first 2 steps, the RASE markup and the OTCVU metadata, have been done manually.
And that's a lot of work.
A lot of work. It requires a lot of expertise, and it can be very time-consuming. So the idea here is to automate those steps using the power of LLMs.
That makes sense. Okay, now for the LLM to learn this complex task, it needs training data. Tell us about the data set the researchers used.
Okay, so the data set they used consisted of 25 text files containing building regulatory information.
Okay.
And these weren't just any random regulations. They were specifically chosen and annotated by domain experts.
So it's a high-quality data set.
Exactly. This data came from the Accord project, which, to the best of their knowledge, is the first and only annotated data set in the Building Compliance Rule Language, or BCRL format.
BCRL.
It's a YAML-based format that was developed by the Accord project to represent these RACE annotations in a machine-readable way.
Okay, so it's basically a standardized way of representing all this information.
Right.
And where did these specific regulatory documents come from?
They came from 3 key regulatory documents in England, M2, which focuses on access and use of buildings.
Okay.
L2A, which deals with energy conservation in buildings,
Uh-huh.
and BV100, which covers fire safety design for schools.
So a good mix of different types of regulations.
Yeah, they chose 25 sections from these documents and had them fully annotated with RACE and structured into those YAML files.
Okay, and what about the characteristics of the annotations? Were certain race categories more common than others?
Yeah, so as we talked about earlier, requirements were the most frequent type of tag.
Which makes sense.
Exceptions were the least common, and selections appeared slightly more often than exceptions. Applicabilities were mainly linked to requirements.
Which again makes sense.
Because they specify when those requirements apply.
Right, so that distribution really reflects the structure of most regulatory documents.
Exactly.
What about the length and complexity of those annotations?
So applicabilities and selections tended to be pretty short, often less than 8 tokens.
Okay.
Requirements and exceptions, on the other hand, had a much wider range of lengths, from a few tokens to over 40.
Why is that?
It's mainly due to the nested structure of the RACE annotations. A single requirement or exception might have multiple clauses and subclauses, each with its own set of conditions.
So the model needs to be able to handle both short, concise annotations and longer, more complex ones.
Exactly.
Okay, so you've mentioned this BCRL format a few times. Why was it necessary to have the specific YAML-based format for the annotated data?
Well, you need a machine processable format if you want to actually use these RACE annotations in an automated system.
Right, plain English isn't going to cut it.
Exactly. And that's where BCRL comes in. It's based on YAML, which, as we discussed, is both human readable and machine readable.
So it's the best of both worlds.
Right. YAML is easy to understand for us humans, but it's also easily parsed and processed by computers, and it's compatible with lots of programming languages.
So it's a very practical choice.
Exactly.
Now, how does this conversion from plain English text into BCRL actually happen?
Okay, so it's a two-stage process.
Okay.
The first stage is all about capturing the structure and context of the document.
Okay.
You identify all the sections, titles, paragraphs, bullet points, the main text, and you arrange them in a nested YAML format.
So you're basically creating a digital skeleton of the document.
Yeah, you can think of it that way. Each element in this structure gets a unique identifier and a type,
Okay.
like document subdivision for a section or statement for a paragraph.
So it's all very organized and clearly labeled.
Exactly.
Okay, and then the second stage is where you add the race annotation.
Right. The second stage is where you actually apply the RACE methodology and populate those YAML elements with the RACE tags and their OTCVU metadata.
And remember, OTCVU, that's object target comparator value in unit. So you're basically adding all the details that the computer needs to actually perform the checks.
Right. And BCRL also introduces this method type attribute, which helps to simplify the process of generating the rules.
Okay. And importantly, BCRL maintains a link between each annotation and the original text.
Yeah, that's really important for traceability.
So you can always go back and see where the annotation came from.
Exactly.
Okay. Now, one of the challenges with LLMs is that they have a limit on how much text they can process at once. Those token limits you mentioned earlier. How did the researchers deal with that?
Yeah, so most LLMs have a limit of around 4096 tokens.
Tokens being units of text.
Right.
And regulatory documents can easily exceed that limit.
Oh, yeah, for sure.
So what did they do?
They came up with a clever strategy called incremental prediction.
Okay, tell me more about that.
So instead of trying to process the whole document at once, they broke it down into smaller segments.
Okay.
The model takes one segment, generates the YAML for that segment, and then that YAML is reinserted back into the model's context, along with the next segment.
So it's like processing the document in chunks.
Exactly. And this ensures that they never exceed the token limit.
It's a really neat solution.
Yeah, and they perform checks at each step to ensure that the annotations from the different segments are consistent.
So it's like building a wall brick by brick.
Pretty much.
Okay, so they've got their data set, they've trained their model using different techniques, and they've figured out how to handle those pesky token limits. Now, how did they actually evaluate the performance of the system? What metrics did they use?
They use two main sets of metrics, structural similarity and text similarity.
Okay, structural similarity, that makes sense. You want to make sure the model is generating the YAML output in the correct structure.
Exactly. And to measure that, they converted the YAML files into graph representations and then used graph similarity algorithms to compare the generated graphs to the reference graphs.
So it's like comparing two blueprints to see how similar they are.
Yeah, the very visual way to think about it.
Okay, and what about text similarity? How did they measure that?
So for text similarity, they looked at the actual content of the annotations, the specific words and phrases that were tagged with the RASE operator.
Okay.
They used standard accuracy, which is simply the percentage of overlapping words between the generated output and the reference output.
Okay.
But they also used a more sophisticated metric called adjusted accuracy. which takes into account how the text is segmented.
Because even if the model gets all the right words, it might group them differently than the expert did.
Exactly. And that would affect the overall accuracy.
So adjusted accuracy penalizes for those segmentation differences.
Right. It's a more nuanced way to measure the accuracy.
Okay, so what were the results? What did they find?
So for few-shot learning, the average structural similarity was 0.69, and the average text similarity was 0.76.
Okay, so not bad considering it only had 3 examples to learn from.
Yeah, the text similarity was actually slightly higher than the structural similarity, which suggests that the model could identify the correct content.
But struggled more with the structure.
Right.
What about fine-tuning? How did that perform?
Fine-tuning showed a big improvement. Both the structural and text similarity scores increased significantly.
So that extra training data really made a difference.
Definitely.
And what about progressive active learning?
Progressive active learning achieved the best results overall.
As you might expect.
After 3 iterations of fine-tuning, expert feedback and retraining the model reached the highest similarity scores.
So that human-in-the-loop element was really crucial.
Absolutely. The model benefited greatly from having experts guide its learning.
Okay, so what are the big takeaways here? What are the practical implications of this research?
So the biggest takeaway is that this approach combining LLMs with active learning is a really promising way to automate race annotation.
And that has huge implications for the AEC industry.
Oh, absolutely. Imagine being able to integrate this into BIM systems.
Yeah.
You could have real-time compliance checks during the design phase.
That would be a game changer.
It would save so much time and effort, and it would drastically reduce the risk of errors.
So architects and engineers could catch potential issues much earlier in the process.
Exactly. And that would lead to safer and more efficient buildings.
Now, of course, there's still some limitations with this approach. What did the researchers highlight?
So one limitation is that the model's performance is still dependent on the quality of the training data.
Makes sense. If you train it on bad data, you're going to get bad results.
Exactly.
What else?
They also highlighted the need for ongoing expert oversight.
Right. The model isn't perfect. It's still going to need human guidance.
Yeah. And then there were the practical challenges of integrating this into existing BIM platforms.
That's a big one.
Yeah. It's not just a matter of plugging it in and hoping for the best.
You need to make sure it works seamlessly with all the other tools and workflows.
Exactly.
And finally, they mentioned potential performance concerns with very large data sets.
Right. As the data sets get bigger, the computational demands increase.
So there's still work to be done in terms of scalability.
Yeah. But overall, this research represents a huge step forward.
It's a really exciting development.
Absolutely.
So for you, the listener, the key takeaway is that AI has the potential to revolutionize how we approach regulatory compliance in the AEC industry.
It's all about making the process faster, more efficient, and more accurate.
And ultimately, it's about creating safer and more innovative buildings.
Exactly.
This research gives us a glimpse into the future of building design and construction.
And it's a future where AI plays a central role.
It makes you wonder what other aspects of the AEC industry could be transformed by AI.
Yeah, the possibilities are pretty much endless.
Food for thought. So thanks for joining us for this deep dive into the world of AI and building regulations.
It's been a pleasure.
Until next time.
See you later.